you also mentioned in your thesis that these solitary waves weren't observed until a later problem arose, including Enrico Fermi. So I'm interested in hearing what the story was there.
Yeah, so in 1953, a couple of people, Fermi, Pasta, Ulam, and a graduate student, Singyu, were working at the Los Alamos National Lab on a computer there that was recently built called the MANIAC mainframe. MANIAC is an acronym that I don't remember what it stands for, but it's pretty funny. And they have still at the Los Alamos um, like National Lab History Museum, they have some of the vacuum tubes from the original MANIAC computer that were the old version of like transistors that we now have in our computers. So those are pretty. I have a picture of myself in front of them, which is great. I cherish that photo. So what they were doing on this computer was they were simulating atoms in a lattice, um, uh, and letting them vibrate and exchange energy between neighboring atoms, essentially. So they modeled the lattice as a bunch of masses with springs in between, and they let it be periodic. So think of it as being like a very large circle where if you look at any single section, it pretty much looks straight. So you have some masses with springs in between, and you let the masses vibrate, and the springs will exchange energy between neighboring masses. So if you let the spring force be linear, Hooke's law, the solution to that situation is well known, and it is because it's linear. It also has this linear superposition principle where you can add solutions together, and you get again like on a guitar string, you have harmonics of this system. But what they wanted to do was make the springs slightly nonlinear. They added a cubic term. So you have Hooke's law, which is a linear term in displacement between the two masses, and they added a little bit like a cubic times some small number to the spring force. And what they expected is that if you start it in one harmonic of vibration, where all the atoms are kind of moving together, eventually that nonlinear term should move energy between harmonics. And eventually you'd get what they call thermalization, where the energy is evenly spread out between all the harmonics. That's what they expected. And the motion just looks sort of random. And they were trying to show this because at the time it was like in statistical mechanics, this is the theoretical understanding, but it still hasn't been shown in any like rigorous context exactly how this energy thermalizes in a system. So they coded it up with the big punch cards and everything, and they simulated this system for a long period of time. And what they found was very surprising to them. They found that it didn't relax to energy being equally distributed between all the harmonics. Eventually, if you waited long enough, all of the energy would go back and it would form the original initial condition they started with. So they started with the energy all in the longest wavelength harmonic. And what would happen is you would see, if you look on the short time, energy would leak out of that harmonic into the other harmonics. But eventually, it would all recollect back into that one initial long wavelength initial condition. And not only that, but it was almost periodic. It was like the time period that it would happen with was like almost the same every time. So they were like really puzzled by this. What the heck is going on? It's a nonlinear system. They expected it just to thermalize and be done, right? So it took a couple more years until Zabusky and Kruskal solved this problem in 1965. They wrote a paper showing that the system of masses and springs, was actually a discretization of the KdV equation. So it's when you model a PDE on a computer can't handle a continuous function. So you have to do what's called discretizing, where you take values of the function at usually like equal time steps, and then you model the derivatives as differences in the function and everything like that. So what they found was that what they were modeling was a discretization of the KdV equation. And when they were able to model it a little bit better in 1965, they found that what was happening was this long wavelength initial condition. It would first steepen on one side, and right when it looked like the wave was about to break, it would actually get a little wiggly, and then you would see these solitary waves split off of the main initial condition. And then you'd see them rank ordered. So the fastest, tallest one would come out first, and then the next fastest, next tallest one would come out second, and so on and so forth. And because it had periodic boundary conditions, they would race around the track, and eventually the fastest one would catch up to the slowest one again, and they would all kind of collapse and come together and reform that initial condition in about periodic time. And so that was pretty surprising, even more surprising than the FPUT problem was originally, because everyone knows we just talked about how these solitary waves are solutions to the KdV equation. That doesn't seem surprising. But the fact that there are multiple of them in this solution is surprising, because this is a nonlinear partial differential equation. There is no linear superposition principle. So I can't just add together two solutions and expect to get another solution, because the nonlinear term messes this up, right?
But you're saying that if I have multiple solitary waves, solitons, as they're called, somehow I recover this linearity, or is it different?
There is sort of a way of thinking about this as being linear, but really what's happening is, if you think about the solitons, if they're far from each other, they're these like localized little humps, right? So if they're far from each other, then if I add those two together, the solution until they come near each other does look like the sum. But when they come and they're on top of each other, the solution is like nowhere near being the sum of the two. Then when they pass through each other, the fast one overtakes the slow one. What you actually see is that if you compare it to just the sum of the two moving at their own individual speeds, the fast one is a little bit shifted forward from where you expect it would be after the interaction. And the slow one is a little bit shifted backwards from where you expect it to be. So there's this memory of the interaction that makes this like a totally nonlinear interaction. But to your eye, it looks sort of linear at some points, and at other points, and then in the middle, it's just like a total mess. Like you can't tell, oh, there's the little one, there's the big one. They're adding sort of coherently in the middle.